Okay, good morning everyone. Welcome to 130B, Quantum Mechanics. So let's start our lecture today. So today we are going to continue our discussion of measurements, and it's all related to Hermitian operators. So last time we have started the idea of Hermitian operators. In order to understand what does it mean by Hermitian, we first need to understand the idea of Hermitian conjugate. So if you have an operator O, there's always a dual operator which is related by Hermitian conjugate. The idea is that if the operator acts on a certain cat state, then the dual operator, the Hermitian conjugate, will act on the bra state such that the action is equivalent between cat and bra. So that's the idea. And then because between cat and bra, what we need to do on the state level is basically to conjugate transpose the state vectors. So on the operator level as matrices, what we also need to do is to conjugate transpose the matrix. So that's the idea of Hermitian conjugate. So every operator as a matrix has a Hermitian conjugate because every matrix you can transpose and then followed by complex conjugation of every matrix element. So Hermitian operator is a special type of operator whose Hermitian conjugate is itself. Later on, we will also learn another operator called the unitary operator whose Hermitian conjugate is inverse as a matrix inverse. So these are the two most important operators in quantum mechanics. Hermitian operator represents observables in quantum mechanics, and then unitary operator represents time evolution or symmetry transformations. So they are all related to this concept of Hermitian conjugate. Why Hermitian conjugate is important? Because it's like the complex conjugate for complex numbers. So if you have a number which is equal, a complex number in general, which is equal to its complex conjugate, then this complex number actually is a real number. So the idea of using Hermitian operator to represent physical observables is because physical observable, whenever you observe it, you never observe a complex number. So that's why people choose Hermitian operator. It's become special. And as we will learn very quickly today, that every physical observable is represented by a Hermitian operator, and the corresponding observation values are the eigenvalues of this Hermitian operator. And there's a very nice property for the Hermitian operator that is all its eigenvalues are real. So for Hermitian operators, its eigensystem has the following properties. All the eigenvalues are real, and all the eigenvectors, if they belong to different eigenvalue, they are automatically orthogonal to each other, and then of course you can choose to normalize them. And then if they don't, and then if they belong to the same eigenvalue, they are not guaranteed to be orthogonal, but you can find all the possible eigenvectors with that eigenvalue and try to orthogonalize them. So they still form an orthonormal basis. So in the end, this Hermitian operator, you can, every Hermitian operator in a finite dimensional Hilbert space, basically you can find a set of eigenvectors for it, and these eigenvectors can be chosen in such a way that it forms an orthonormal basis. And this is a very nice property that means every state in the Hilbert space can now be represented as a linear combination of the eigenvectors of a Hermitian operator. And the Hermitian operator itself can also be represented in its own eigenbasis as a linear superposition of these basis, you can call it basis operators. Previously, when we talk about operator, we learned that operator can be written as a linear superposition of an outer product of states. So outer product, by outer product, I mean this cat state product, this bra state, right? So if you first ignore this O here, this cat state, or maybe look at up there, cat state product bra state, this thing itself is also a matrix, and it is an operator. And then the meaning of this operator means that this operator go and search for this OK eigenstate or eigenvectors, and then if it matches OK eigenvector, it returns the eigenvector itself. So basically, that's why summing over all these basis operator is an identity operator, because this basically means you go and search for every eigenstate and then keep it the same. Then that basically means you are doing nothing to the states, because any state is a linear superposition of these eigenstates. And then if every eigenstate remains the same under the action of this operator, then this operator does nothing to the linear combined state as well. But if you have this operator itself, then the action goes like you search for the eigenstate and then multiply by OK and then return the eigenstate. It's like you try to match this state and return the product of these two, which is OK scaling on this eigenstate. And that is indeed what is the meaning of the eigenequation, right? When OK is said to be a case eigenstate of this operator O, we mean that the operator O acting on this state should be the same state followed just by rescaling a factor OK. So that's why in its own eigenbasis, the operator can always be written as a summation for all eigenstates, and for each one of the eigenstates, you basically just amplify the states by this amplify the eigenvector by the eigenvalue, basically. So this OK is the eigenvalue. I mean, in the middle, this number is the eigenvalue. This cat OK, we basically use the eigenvalue to label the state. That's a common practice. So this is the corresponding eigencat. This is the corresponding eigenbra. And then if you put cat, eigenvalue, and bra together, summing over all the eigenstates, and then that reconstructs the operator as a matrix for you. So this formula is also called the spectral decomposition, because all the set of eigenvalues of the operator is called the spectrum of the operator. And then this is spectral decomposition, meaning that you can decompose the operator as a summation of things. Okay, so this is one thing I want to emphasize. And then in this eigenbasis, the operator looks like a diagonal operator, because it basically takes every eigenstate multiplied by the number and return it, and that's it. If you represent these eigenstate as one-hot vectors, then the corresponding matrix representation of the operator will be diagonal. Of course, at the very beginning, when we write down the operator in certain chosen basis, it may not be diagonal, but we can always find basis transformation, meaning that we abandon the previous basis choice and we choose a new set of bases. The new set of bases basically aligns all the eigenvectors along the direction of your axis. It's like choose another frame of coordinates such that all the axis aligns with one eigenvector. So in that very nice choice of the coordinate systems, then the operation of an operator which can be brought to diagonal. This matrix can be brought to diagonal. The process of finding such a new basis or performing such a basis transformation to bring the operator to diagonal is called the diagonalization. Basically, that's finding eigensystem. That these two words are of the same meaning. It's as long as you can find the eigensystem, you can diagonalize the matrix. Diagonalization is very useful because it helps us to construct operator functions. Previously, we learned that you can also define functions for operator just like we can define functions for numbers. When we define functions for numbers, we basically use the Taylor expansion. And it is the same idea. You can use the same Taylor expansion, whatever the function, how it expands. For real numbers, it expands the same way as for the operators. And only for the operators, all the power of the operator is basically a matrix product for example, n's power is like matrix product n times. So you need to combine all these power of operators and then following the Taylor theory to define the function. And that seems to be a very tedious procedure. And then it's very difficult to compute. But what diagonalization brings us is it allows us to choose a new basis to represent the same operator function. And the result of the operator function is still an operator, but the new operator can be constructed in such a way that you only need to take the bra, eigenbra, and eigencat and eigenbra, and then replace the eigenvalue by whatever this function acting on the eigenvalue, right? The function will map the eigenvalue to new real values. suppose this is a real function, and suppose all the eigenvalues are real, at least for Hermitian operators, then basically that's what we mean. Of course, this formula is more general than Hermitian operator, even if it's a unitary operator. As long as you can have a spectral decomposition, you can use it to define these functions. So that's what we have learned about last time. Any questions? So here comes the homework 3. So I'm sorry that there will be many homework in today or maybe next lectures because the homework was not distributed evenly throughout the lectures. So I give you enough time. You can there's no deadline or there's no hard deadline. There's a soft deadline. So you can take your time to finish this homework. So let's take a look at homework 3. What it is about. It is saying that suppose there's a particle that can travel on a graph, which means that you can see there are 8 different points on the graph, right? And then connected by lines. And a particle is like a single dot. They can jump from one point to another point, and then to other points. It can like do something like that. Can jump or hop or travel on the graph. So that is cat eye state. Denotes the state that the particle stays on the ith vertex of the graph. So this graph contains the vertices, which are these points, and the edges, which are the connections or links between the points. Okay, so this Hamiltonian, which we denoted as H, you don't need to understand its meaning. It's just another Hermitian operator. For now, we can construct a Hermitian operator that represents the particle hopping on the graph. Meaning that for every I and j that are connected by a link, we basically write down a term like that. That means this term basically means we can take the j state and then move it to the I state, meaning that we can take the state where the particle is living on the j side and then move it and then return the new state where the particle actually appears on the I side. This basically describes a process that you take the particle from the j side to the I side. And then this describes the inverse process, which you reverse this jumping, and then the particle travel from I to j backwards. So for every bond I and j that is connected, you write down a term like that. For two sides that are not directly connected, for example, this side, if this is I, this is j, then there's no such a term because these two sides are not directly connected by a link. So this summation is summing over all possible links between the sides on this graph, basically. So this operator describes the quantum process for the particle to tunnel from one vertex to the other vertex, and the summation sum over all the possible links on the graph. Okay, so the homework is like this. The first problem is try to represent this operator as a matrix in the basis of I. So every I state is a distinct reality because it corresponds to particle living on a different side, and then you can measure the particle's position and determine which side it is on. So every different particle on different sides is a different, or different vertex is a different state, a distinct state. So they are all orthogonal to each other. So you can write down an 8 by 8 matrix because altogether we have 8 sides, and try to write that down. And then there's something you can try to do it by hand is to, or you can use a computer program, but it's more recommended to use a program, Mathematica or anything, or Python you can also do, or MATLAB, whatever mathematical software, and type in the matrix and try to diagonalize the matrix and find its eigenvalues. And we are only interested in its lowest and second lowest eigenvalues. And then you can try to, also every eigenvalue corresponds to eigenvectors, right? So this lowest and second lowest eigenvalue correspond to two different eigenvectors, and try to plot them. Eigenvectors has, this eigenvector, I can tell you, they are all arrays of numbers. Each eigenvector is an 8-component vector, and then the vector component turns out to be real in this case. They are all real, and then so you can plot them in terms of, for example, you draw a graph and then put the color on the vertices. Maybe red color means that the value is positive, blue color means that the value is negative. for these eigenvectors components. And then you can try to visualize that, try to see what you find for the lowest and second lowest eigenvectors. I can tell you the result is that what you will find is that it automatically color this part. For the lowest eigenvalue, every site will be colored red. Basically, every site will have a positive component in its eigenvector. And for the second lowest eigenvector, what happens is that all the left-hand side, all this cluster is red, all this cluster is blue, or something like that. Automatically, this eigenvector will color two different clusters differently, meaning that the components of the eigenvector will be positive on one side and negative on the other side. So it automatically splits the clusters apart. This is very magical. This is a way to actually do clustering. If you have a bunch of objects interconnecting with each other, this is like these peoples form a community, these peoples form another community. Within the community, two peoples are all, every pair of peoples are friends to each other, but within these two communities, only the community leaders talk to each other. The other people in the community, they never see the other, they don't talk to each other between the community. So the link between the community is very weak, and then these whole 8 peoples together forms 2 groups or 2 communities. And in many cases, we hope to automatically distinguish these 2 communities, label people by their community. So this writing down this graph as a matrix and then put a quantum particle hopping on this graph basically is a quantum mechanical process which allows us to automatically distinguish different communities. So that's called spectral clustering. That's an algorithm. We are basically repeating this algorithm in this homework. The purpose of this homework is as follows. I think there are several interesting techniques you can practice. First of all is how to understand these basis operators as quantum processes, right? And then how to translate such an abstract notation into a matrix which you can actually write code and then you can actually compute. How to translate it into an 8x8 matrix. And then we will also practice the technique of diagonalizing the matrix or finding its eigenvectors and values. Of course, maybe you don't want to do it by hand. You can write a program to do that. And finally, we will try to see what's the physical meaning of these eigenvectors by visualizing them on the graph again, and then you will get some understanding of spectral clustering algorithm, although I'm not going to prove that, but I think those are the goals of this homework. So any questions? Okay, yeah, take a try of this homework. I think it's an interesting one. So apart from these very complicated 8x8 matrices, let's look at some eigensystems which we can really compute by hand, which are eigensystems of Pauli operators. So Pauli operators are these 2x2 Hermitian matrices, which are operators defined for qubits. And then there are 3 of them, sigma x, sigma y, sigma z, and their matrix representation are as follows. The nice property of these Pauli matrices is for each Pauli matrix, the eigenvalue turns out to be only +1 and -1. There's only 2 eigenvalues, and the 2 eigenvalues are +-1. And the corresponding eigenvectors, people usually denote the eigenvectors of sigma x as plus and minus. The eigenvector of y is I and I bar, and this is 0 and 1. Remember, we have homework 1, which I use the same notation. So you already, it's a cheat, actually. So you can already look at the answer is already here. But I think homework 1 is asking you to, even if you know the answer, and try to provide some argument or try to provide certain checks on, yeah, these answers indeed reproduce the relations between these states that are stated in the homework 1. But what I want to talk about today is not about how to find these eigenvectors, because you can anyway put into a mathematical program and find them, or you can maybe, I think the TA in the discussion section also explain how to find it. I think what I want to emphasize is this projection operator. Remember, previously we say that every Hermitian operator admits a spectral decomposition, meaning that it can be written as a summation of these cat and bra operators, which actually we called it projection operators. You are linearly combining these two projection operators with the eigenvalues, with the corresponding eigenvalue, meaning you take this projection operator, multiply by this eigenvalue, and take this projection operator, multiply by that eigenvalue, and sum them together. The result will reconstruct this matrix. And is that the case? That's actually the case. So first of all, let's see how do we construct this projection operator. We will take the cat state, and then we will construct its corresponding bra state by transpose and complex conjugate, right? So we will have two. So this will be 1 over square root 2, 1, 1, and 1 over square root 2, this 1, 1. Horizontally. So this 1 over square root 2 multiply together into 1/2, and then this 1, 1, and 1, 1, if you do a matrix multiplication, first element is 1, second element is 1, and then the next element 1, the other element is 1. So that's here. So if you have a -1 here, if it's minus, basically you get 2 minus sign here. So that's how we construct this projection operator. And you will find, yeah?
Projector matrices, is that a minus sign and then it is just like subtraction, or is it meant to be?
It meant to be the eigenvalue times the spectral decomposition formula is okay. The minus sign is this okay. Because for the plus state, the eigenvalue is +1, and for the minus state, the eigenvalue is -1. Look at the table. And then you add them together. It's actually a plus sign, but because the eigenvalue is -1, so it becomes a minus sign.
Oh, I see.
Yeah.
So, but it is just using the summation formula.
It's using the summation. This is the sum. This is not subtraction. And then all the minus sign coming from these eigenvalues. And it is because the eigenvalue is -1 for this minus projection operator that it appears as if you are subtracting these two eigenprojectors together. Yeah. So that's what I want to say, that you can, for every Hermitian operator, apart from trying to find its eigenvectors, for each eigenvector, you can also construct a projection operator called eigenprojector. Why do we call it projection operator? Because the projection operator really is projecting things down to this eigenvector's direction, because it looks like its function is like a filter. Basically, every projection operator filters out subspace. Within the subspace, the state vector doesn't change, but out of the subspace, the component of the state vector will be projected to 0, basically. So, for example, this plus projection operator basically projects out this 2-dimensional Hilbert space and then project it to the 1-dimensional subspace specified by this vector. So, any linear combination of this plus and minus cat vector or cat state, if you act that state by this projection operator, the projection operator will selectively forget about this minus state because the minus state is orthogonal to that, so there's no action. It will selectively choose the plus state and return the plus state itself. So essentially, any linear combination of these plus and minus, after acting by this projection operator on the cat state as a linear combination of them, you will only get the plus with a coefficient in the front, basically. So that's why it's a projection operator. And the same argument applies for the minus state projection operator. And the spectral decomposition, this formula says that the original Hermitian operator can be reconstructed by linearly combining all the eigenprojectors with their eigenvalues as coefficient. These are the eigenprojectors, and then in the front is the eigenvalue. And you can see it's true. It's true in the sense that you really take these two matrices, subtract them with each other, you really obtain this matrix. And you can do the same exercise for all the other matrices, and it's easy to check. The reason that this projection operator basically single out, for example, the plus state, is because the plus state, for example, is the +1 eigenvalue, the eigenstate of sigma x with eigenvalue +1. That means if you try to apply this projection operator on the plus state, what happens is that this sigma x operator will act like a scalar multiplication on the states, on the plus state. So it will be a +1. So this formula reads like 1 + 1 over 2. So on the plus state itself, acting this projection operator doesn't change it. But if you act this projection operator on the minus state, sigma x will behave like a -1. So 1 - 1 divided by 2 will be 0. So if this projection operator acting on the minus state, it will quench the state, basically. So that's why this projection operator, on one hand, you can write it as a matrix like that. On the other hand, you can also, at a very abstract level, you can write it as a linear combination of identity matrix and the sigma x operator, basically, identity and sigma x operator. So this minus projection operator is identity and sigma operator combined in the other way. Yeah. So you can see that there's a similar idea holds for Pauli y, which you can check. You can really check that 1 plus sigma y divided by 2 is indeed this projection operator because sigma y is there. Identity operator plus sigma y operator is this part, right, divided by 1/2. So you can really check that for every Pauli matrices, no matter it's X or Y or Z, its eigenprojector always take the form of 1 plus or minus, depending on which projector you are talking about, and then this operator divided by 2. This seems to be, and furthermore, if you combine these two projection operators with the corresponding eigenvalue coefficient, you will see immediately with a very simple algebra that you will recover the original operator. These are all things to be trivial because x, y, z, anyway, these Pauli operator, you can diagonalize them maybe easily. But it becomes more and more useful when we talk about generic Pauli operators, which is a linear superposition of sigma x, sigma y, sigma z. Remember that this n dot sigma is basically nx times n dot sigma is nx sigma x plus ny sigma y plus nz sigma z, which is another 2 by 2 matrix, which can be very complicated if you write down its matrix element. And if you even try to diagonalize the matrix and try to find its eigenvectors, oh, that's terrible. So you can try that. You can try write down this 2 by 2 matrix, type it into Mathematica, and try to diagonalize it with the generic nx, ny, nz. You can put them as symbols. Mathematica can do the symbolic diagonalization for you, and you can just take a look at the eigenvector. I guarantee you don't want to look at it a second time. So it's so complicated that people have a very difficult time of calculating them. But in many cases, in quantum mechanics applications, we have to calculate these eigenvectors in order to understand what the state the system is in, right? So that actually says that sometimes these ket vectors, state vectors, not easy to compute. But it turns out that their projection operator is so simple. As you see the previous examples, I think you have already, from the previous example, you have already learned that very likely, this projection operator for a generic n dot sigma operator is basically 1 plus or minus n dot sigma divided by 2, depending on which eigenstate you are talking about. Even for n dot sigma, as long as n is a univector, this operator also have eigenvalue plus minus 1. And then depending on the eigenvalue, there's plus minus 1 eigenvectors. And for the ket vector and its corresponding bra vector, they form an eigenprojector associated with eigenvalue plus minus 1. And this eigenprojector has a very simple formula. So this is saying that sometimes we can avoid computing the eigenstate, but still get useful information about spectral decomposition. Because all we want to obtain in the end is how to decompose this operator into matrices, basically. Because once you know how to do this decomposition, you can You can do operator functions, for example, because you only need to now, instead of linearly combine this projection operator with their eigenvalues, you linearly combine the projection operator with function acting on the eigenvalues if you are talking about operator functions of this operator. So using this projection operator, it's very convenient to reconstruct this operator and even its functions. Okay, that's all I want to advertise. Okay, so that's all I want to say about Pauli operators. And this table is important. Hopefully, you can all figure out what is there. And then this formula is also important that hopefully you can understand how to construct projection operator, at least for Pauli operators. Okay, so with that, let's finally start our discussion of observables. Any physical observable, that becomes the very important postulate number 2. So recall that the postulate number 1 is about states. It says that every quantum system, the state of a system is described by a ket vector, right? So the postulate number 2 is describing observables. The vectors describe the state, and what describes observables? We want to make observation of the quantum system, right? So any physical observables of a quantum system is described by a Hermitian operator, very importantly, Hermitian, represented as Hermitian matrices acting in the associated Hilbert space. So basically, in one sentence, observables are matrices. So in quantum mechanics, and these matrices, very importantly, are Hermitian such that its eigenvalues are real. So consider a Hermitian operator with eigenvalue OK and eigenvalue OK ket. Forget about this. This is about degeneracy. I'm not talking about that. Sorry for that. And then you can have a spectral decomposition of these of these operators. Like that, and then for any Hermitian operator, you can write it in this form, and that basically means that if this operator corresponds to a physical observable, in the sense that all the possible measurement outcomes or the observation values of this observable is given by the eigenvalue, meaning that if you observe the system with you design an experiment to observe this observable of a quantum system, and the experiment will only tells you that the system has this observable being taking certain value, and this value can only be chosen from the eigenvalues of the corresponding operators that represent this observable. And then the measurement projects or collapses the quantum state to the eigenspace spanned by the eigenvectors of the corresponding measurement outcome. So in this case, if there's no degeneracy, meaning that every eigenvalues are different, and then every eigenstate has a different eigenvalue, then every eigenvalue specifies a corresponding eigenstate. If you observe certain eigenvalue, you can uniquely identify the eigenstate correspond to that. And then when you observe that eigenvalue, the system will collapse to the corresponding eigenstate, no matter what state the system was at the beginning. But if there's degeneracy, things will be more complicated. These are there are several eigenstates correspond to the same eigenvalue. They actually span the eigen subspace. And then the state will be actually projected to this eigen subspace. Don't worry about that. We will talk about the details very quickly. So this is an overlook of observables. Observables are Hermitian operators. But this doesn't tell us how measurement happens. So immediately, this postulate 2 is followed by postulate number 3, which is about measurement. Given a quantum system in a state, so this postulate is talking about the interaction of the state with observables. So state is a vector, observable is a matrix or operator. Then, given the state, and after specifying the observable, we want to do two predictions. One prediction is what's the probability to observe the measurement outcome. Because when we measure this observable, as postulate 2 asserts, that the measurement outcome can only be the eigenvalue of this observable. this OK. And the probability based on this given state, the probability to observe this measurement outcome is given by the norm square of the scalar product between the eigenstates of OK with the original state psi. This basically follows the Born's rules, which we talked about at the very beginning. We say that given one quantum state, the probability to observe the system in the other quantum state is given by its overlap and then norm square, right? It's given by the fidelity between these two states. So that's the same principle here. So now all these OK states form a complete set of bases. You want to identify, you want to know what's the probability to collapse this original state into each one of the basis state, then the probability, which is a conditional probability, conditional on your knowledge that the system was originally in this state. The probability to observe OK is like that. And after OK being observed, the system will collapse to this OK state. Okay? So there are several comments of this postulate. First of all, in quantum mechanics, there's actually no way to tell for certain which outcome will actually be observed. It's unlike in classical physics, you observe something, you get a definite number. In quantum mechanics, you get a probability distribution, and then nature will sample the answer for you in following this conditional probability distribution. And the conditional probability distribution is the only thing that we can predict in quantum mechanics. So it's intrinsically random and stochastic. Upon observing this observation measurement outcome, the quantum state will be updated. This process is known as the quantum state collapse. It gets updated from the original state to the new state, where the new state corresponds to the eigenstate of the eigenvalue that you have observed. It's like taking the state, and then if you measure O, and then, of course, with this probability, you can observe OK. And once you confirm that you already observe OK, that's already the result, then at that point, you should think that the state has been collapsed to the eigenstate, which is also labeled by OK, which is the corresponding eigenstate with this eigenvalue. So the original state is called the prior state, or the pre-measurement state. The state after measurement, which it collapsed to, which is always an eigenstate of your observable, is called the posterior state, or the post-measurement state. Okay? This idea of prior and posterior actually originated from the classical probability theory. So there is a Bayesian view of this quantum state collapse. I know this process is very it's a very difficult to understand process because we never talk about in detail how this happens. Actually, people don't know how quantum state collapse happens in full detail. For example, is it a dynamics? Does it take time? When you make observations, does it collapse suddenly, or it's a process? Or if I make a measurement and stop it in the halfway, does the state collapse halfway or something like that? So these are all frontier questions in research that people haven't figured out. But there's, I think, a nice view of this process, maybe that helps, is the idea of a Bayesian view of probability theory, which dates back before quantum mechanics. Before quantum mechanics, when people try to understand random process and use probability to describe randomness, they already have these two different views. One is called a frequency list, or people which take an idea of viewing this probability as a limit of frequency. For example, if you want to toss a coin, which can either be top or tail, right? And then you can do this experiment 100 times and then collect the statistics. Maybe 49 is up and then 51 is down, right? Then you can say, okay, in terms of frequency, the frequency of being up is 49 over 100, and then the other one is 51 over 100. So if you take the limit that you can make a lot of experiments, and then in the limit that the experiment number goes to infinity, that this frequency converge to a value which is called probability. So this is the conventional or classical idea of probability distribution. But it doesn't work very well in some very extreme case. For example, we know that if a coin is balanced, that means it has half and half probability to be up and down. You can toss it 10 times, for example, And then you can ask a question, if I do this independent experiment 10 times, what is the probability that every time I get a up, I get a top, right? The probability will be extremely low for that case, because that will be 1/2 to the 10th power, which goes like almost like 1,000. So if you just do 100 experiments, maybe you never see this happen in this 100 experiment, right? You can even move this 10 to 100. That will be terrible. This will be a huge number on the denominator. No human being can ever be possible in their lifetime to complete this kind of experiment. So you will never observe this event happening in the experiment, so you can't do any meaningful statistics about that. But how come we can actually predict this probability distribution? That we know that if you do this tossing the coin 100 times, and the probability that every coin is up, every time is up, is so low, how do you know such a rare event? That means probability is not objective. It's not coming from statistics. It's not doing experiment and take the statistic or take the limit of the frequency. Those ideas are all wrong. Probability is a subjective understanding of the system. It's our human understanding, human's view, your knowledge about the system. The fact that you think that a coin, if you toss it, has 1/2 to 1/2 probability is because no one tells you that there's a difference between up and down. If there's no such a knowledge, then based on this null knowledge hypothesis, then the most reasonable assumption of probability distribution is 1/2 to 1/2. The reason that we believe that tossing a coin has an even probability distribution is precisely because we don't think there's a difference between up and down. If we have some knowledge, for example, this coin has been made in such a way that the bottom is heavier, such that when you toss it, you have a larger probability to see top, for example, then if you have that knowledge, given that knowledge, you need to update your view of probability. Your probability changes with your understanding of the system. This is called the Bayesian view of probability theory. It is no longer doing experiment, no longer taking statistics of frequencies and take the limits, because you can never take limits do the experiment for things like that, but you can still estimate its probability. It's an estimation. It's humans' subjective view. So that applies for classical probability. The same idea goes to quantum. Quantum state is simply the quantum way of representing probability. And quantum states represent our subjective knowledge of or belief about the quantum system. It does not necessarily correspond to the objective physical reality. So it is all because we have been making measurements or observing the quantum system from time to time that we collect the knowledge about the system, and based on the knowledge, we establish what should be the quantum state about the system. And then maybe at the beginning we don't have any knowledge. At that point, we should assume that the system is in certain prior state, which is completely random. But then as we make more and more observations, we should update our prior state to posterior state. And this process doesn't happen in reality, it happens in your mind. So measurement provides new information that forces us to update our belief inside our mind, and this collapse happens in our mind, in our knowledge space. So it is these updates of our belief that collapse the quantum state. So measurement postulate simply tells us how to update the quantum state given the observation in a logical, consistent manner. Yeah, that's the modern view of quantum state collapse. It's not happening in the reality. Okay, so in the last 7 minutes, I want to discuss about what happens if there's degeneracy. So we say that if you observe a quantum system in a certain observable, you can the measurement outcome will be a number which corresponds to the eigenvalue. But sometimes this eigenvalue may have n-fold degeneracy, meaning that there will be n orthogonal eigenstates which correspond to the same eigenvalue, whose eigenequation looks like that. So it's the same operator acting on n different orthogonal states, but they turns out to be all of the same eigenvalue, all gets multiplied by the same number. If this is the case, then if we measure the observable and it turns out that we indeed observe this outcome, then there's some ambiguity, right? We don't know which state the system will collapse to because there are n of them. which correspond to the same eigenvalue, just given the fact that you observe that eigenvalue can't specify which state should be chosen, right? So if you start from your initial understanding of the quantum system, which is described by the state vector, we need to compute what is the probability to observe this measurement outcome, and we also want to compute what is the posterior state. The way to do that contains 3 steps. Step 1, try to compute the scalar product of your initial state with each one of the eigenstate in that eigen subspace. So this M index basically, so this OK labels the eigenvalue, M labels the degeneracies within this eigen subspace. So that means you can basically take the state and expand it as a linear combination of all these eigenvectors with the corresponding coefficient. And the coefficient is simply given by the scalar product of the state with the corresponding eigenvector. That's what we learned previously for as long as these eigenvectors forms orthonormal basis, which is actually the case for the Hermitian observables. And then we only care about those components in front of the eigenvector, which correspond to the eigenvalue OK, which we try to predict, right? For the other eigen subspace, it's not so important, because eventually the probability will just be given by the square norm square of this projection of the original vector in this eigen subspace. So which goes like this. So I think maybe a pictorial way to think about that is like, for example, you have some subspace which has degeneracy that's like O1, the first state is along this direction. O1, the second state is along this direction. Maybe there's an O2 state, which O2 is different from O1, which is in the third direction. And then you have a generic state, which is like a vector like that. It has a projection within this O1, O2 plane, and then it also has some projection in the other direction. So these are the other states in that formula, which we don't care. We only care about the projection of the original state in the subspace spanned by all the state vectors which are degenerate in this subspace that correspond to eigenvalue O1. Okay? So this is the way to compute this projection. And then this is the way to compute what is the length of the vector. This vector itself is a unit vector because every state vector will automatically assume it to be normalized. But when you project to the subspace, it's no longer a normalized vector, it will be shorter. And then it depends on the square of this length, how long this vector is, actually how long, and then square it. And then this basically gives you the probability distribution. So if the vector has a longer projection in the subspace, meaning that the vector is very close to these states in the subspace, right? So there will be a larger probability if you start from this vector, start from this state vector, and observe this eigenvalue correspond to this degenerate subspace. If somehow this vector is kind of perpendicular or orthogonal to this subspace, then the probability to observe this eigenvalue will be negligible. In the orthogonal case, it will be 0. So that's the idea. So the second step is to aggregate these coefficients and compute the probability. And the third step is that the state will do what? It will, after observing this eigenvalue, it will collapse to the projection of the state in the subspace, which is given by this formula, which is basically this alpha m, summing using alpha m coefficient to combine all these eigenvector in the subspace. Well, this alpha m, I put a tutor there. This is only to renormalize the state because this, if you just use the original alpha m, this is just part of the state, and the sum of this component is not 1. So I mean, a sum of norm square is not 1, so you need to renormalize this coefficient, and that's it. So this is all we need to do, and then through these 3 steps, you can start from any state, and then given the spectral decomposition of your observable, meaning that given the spectral decomposition, this sentence means that you know what are the eigenvalue and the corresponding eigenvectors. then the first step is always represent your state as a linear combination of all the eigenstates of this observable, and then figure out what are the combination coefficients. And then based on the combination coefficient, grouping all these coefficients that correspond to the same eigenvalue together, in that way you can compute what is the aggregated probability to collapse to that state. This basically is the idea that if there's multiple eigenstates correspond to the same eigenvalue, then in order to observe that eigenvalue, you have multiple possibilities, right? You need to sum them together. So that's the total contribution to the probability of observing that particular eigenvalue. But after observation, the state need to collapse, or another way of saying, you need to update your belief of the state in your mind. And then the way to do that is to project the state into the subspace specified by this eigenvalue, which you observe, and then renormalize the state such that the probability becomes 1 again. So it's always a good practice to just normalize the state after the projection, okay? So that's it for today. Let's leave homework to the next lecture, okay? Thank you. Yeah.